So what I want to do is to talk about a little bit about what is finite geometry. In fact, there is no such a thing as finite geometry. There are finite geometries, and there are lots of them. What we start with is just a set of points. We call them points, but they don't have to be points as we know them. They can be anything. People, I can think of you as the set of points. All people here are points. And then we form some subsets of those points, and we call those subsets lines. So I might as well say, all people who sit in the same row form a line. So how many lines do we have here? How many lines? Emily, how many lines?
4.
Yeah, 4 lines. 4 lines. Well, we have one particularly small line that consists of 1 point, right? Then we have another line that consists of 2 points, and then we have a nice big line consisting of 5 points, and then a little smaller line of 4 points. Good. So we are going to, you form a geometry. This is a geometry. Whenever we have two sets, one which is called points, and another the set of subsets called lines, we can say, well, that's a geometry. It's a finite geometry. In fact, what makes it finite is the fact that we have finitely many points. If we had infinitely many people here, it would be hard to squeeze them in, but just imagine that we have infinitely many people, then we would have a geometry consisting of infinitely many elements. Well, if we simply allow any set of points and just any lines, we can ask, what are the properties of this particular geometry? And sometimes there will be some interesting properties, but there is a different approach, and that different approach is what really makes this subject interesting. We might, ahead of time, decide that we want our set of points and lines satisfy certain properties that we are going to call axioms. And then we can ask all sorts of questions about this geometry. To begin with, we might ask, well, with the set of axioms that we chose, can we really construct such a geometry, or it is impossible? Now, if I told you, I have a geometry that consists of 2 points and 25 lines, and every line has at least 1 point, is it possible to construct such a thing? Is it possible? No, it's not possible. So we say that this set of axioms is inconsistent. It's kind of silly to ask that to set these axioms, because it's impossible to have any representation. But we can have some nice sets of axioms, and we can construct representations. In the beginning of this handout, I started with giving a number of examples. So let's switch to something a little bit more interesting. Let's switch to more general type of geometries. And the type that I want to discuss is called near linear space or linear space. And it's on your handout. It's on page 3. It's the little section is near linear and linear space. Well, there are very few axioms for near linear space. What are the axioms for near linear space? Only 2. In a near linear space, every line has at least 2 points. And what is the second one? What's the second axiom? Anybody to read it out loud? Emily.
2 points are on at most one line.
Thanks. 2 points are on at most one line. Oh, well, we have a couple of models here. Is this a near linear space? Is it true that every line has at least 2 points? Yes or no?
Yes.
Yes. Is this true? Is it true that every 2 points are on no more than one line? Yeah, these 2 points are on one line. These 2 points are on one line, and these 2 points are on one line. So this is a near linear space. How about this one? Is this a near linear space? Yes or no?
Yes.
Yes. Again, both conditions are satisfied. Now, maybe everybody is a near linear space. Okay, let me show you an example. Suppose that I have something like these 3 points are on a line, and then these 2 points are on a line. Is this a near linear space? Why not? Well, I have 3 points here. I have 2 points on this line, so the first axiom is satisfied. Yeah.
You have 2 points on two lines.
Yeah, the second condition is not satisfied. These 2 points belong to 2 different lines, so this is not a near linear space. Well, how about something like, oh, well, I can fix it, can't I? What if I just do something like this? Is this a near linear space? Why not?
Well, that line only has 1 point.
This line has only 1 point, so this is not. This is the first condition is not satisfied. Okay, so this is not a near linear space either. Well, too bad. I'm going to talk about generating set. If we start with a geometry, well, probably I need to give you some good example. Let me start with an example which looks somehow like this. We have points 1, 2, 3, 4, 5, and 6. To begin, so we have that many points, 6 points. How many lines? Have 1, 2, 3, 4 lines. This is a near linear space, but not a linear space. But it is a near linear space. You can check that all the axioms are defined. Now, I'm going to just show you what it means for a set to generate something. If you start with subset of the points here, let's start with a subset of points. Let me start with a subset of 1.6. If this point has no lines through it, it generates just itself. If there is, if we have a couple of points in a set that lie on a line, we have to add to that set all the points on the line. So if I have one single point, 6, it generates itself. If I take a point 2, what does that point generate? Now, let me repeat. You start with a set. Start with a set. If you see 2 points in that set that belong to a line, you have to add all points on that line to the set. And then you just continue doing that until you are done. So if you start with 1 point, what do you need to add?
Points 1, 3, and 4.
What?
Points 1, 3, and 4.
Now, let me repeat. You start with a set of points. I'm not saying how many points in that set. Then you look inside that set. If you pick 2 points from that set, if they lie on a line, you have to add all points on that line. Okay, so what does that point generate? Just itself. There is no line. So it just generates itself, and 6 generates itself. What does point 4 generate? Just itself. So every point, if you have just one single point, it generates just itself and nothing else. All right, now let's start with points, let's say 5 and 1. What does that set generate? Is there a line between 1 and 5? No, so we don't need to add anything. If there is no line that is lurking there, we do not add anything. So if we want to add the second line, we take 2 points from this line and then throw in 1 point from that line. But in order to get 6, we have to start with having 6, because 6 cannot be generated by anything. So this is the smallest number of points that we need to start with to generate the entire set. Yeah.
If you just had 2, 4, and 6, wouldn't that?
If you have 2, 4, let's look. We have 2, 4, and 6. Let's start with 2, 4, and 6. We have 2, 4, and 6. What is the closure of this? 2, 4, and 6. Nothing else. Nothing else. We have just 2, 4. They are already online and they're happy. They don't need any companions. And 6 is all by itself. Okay. So this is the smallest number in a set that generates the entire set S. Now, the definition of the dimension is it is 1 less than the smallest number of points that generate the entire space. So what's the dimension of that creature?
3.
3. The dimension of this is 3. What's the dimension of this? What's the dimension of this one? Yeah.
2.
The dimension of this one is 2 because how many points do you need to generate it? All 3 points. All 3 points generate that space. You cannot get away with less than 3. If you have 2, it generates just that line. In fact, any 2 points that are on a line generate that line. Any 2 points that are on a line generate that line. What does it tell us about the dimension of a line? If you have one single line, if your geometry consists of one single line, what is its dimension? 1. Always. No matter how many, whether it is infinite or finite line, the dimension is 1. What is the dimension? Okay, so the dimension of this one is 2. What's the dimension of this one? What is the dimension of this line? 1. I leave it for you to think.
No, but by the definition that every 2 distinct points determine a unique line, every line can only have 2 points.
Right, because if you have like
Unique
But then that
points,
proves that
these
they'll
must
have to
determine
go
lines.
for a
That's
line.
for points,
like that.
No, but see, then that intersects that, and that has to go.
There must be this line, and there must be this line as well.
So you have to have every single possible line.
Yes, that's true. Then every 2 lines meet at a point. You cannot have parallel lines. All lines have to be meeting. So far so good. It looks like we have satisfied this axiom and this axiom, right? How about this one?